Hey everybody, and welcome to our next video in Unit 11, which is all about 3 of the gas laws. So we're not going to do them all in one video because that would be a very lengthy video. But in this video, I'm going to cover Boyles Law, Charles's Law, and Gay-Lussac's Law. Before we get into that, however, let's talk about pressure. So when we talk about these gas laws, we're going to talk a lot about volume, which we've done already. It's how much space something takes up. And we're going to talk about temperature, which of course temperature is the measure of the kinetic energy that the particles have. The higher the temperature, the more kinetic energy particles have. Pressure is new for us, however, at least if you had me. We didn't talk about pressure very much in Chem 1. But pressure is the force per unit area that's exerted on a surface. In chemistry, it's typically the pressure that's exerted on the container walls of a vessel. So if I have a gas that's present in, a beaker, let's say with a lid on top so they can't escape, the pressure of that system is the force that those gas particles are exerting on the walls of the beaker. And there are so many different units for pressure. You will not have to memorize these, but I will give you these conversions to and from one another as you're learning these, because I don't have them memorized. I don't expect you to have them memorized, but you might memorize some of them just because we use some of them a lot. But this little area right here is the one that I tend to focus on. So let's see if I can highlight this for you here. Let's just get the pen. And I just want you to know this right here. This is crucial. So in this section, what you need to be familiar with is that 1 atmosphere of pressure is equal to about 760 millimeters of mercury. And 1 atmosphere is the atmospheric pressure that's at sea level at 0 degrees Celsius. So if you were in Hawaii on the beaches at 0 degrees Celsius, which seems not very pleasant because that would be 32 degrees Fahrenheit, which is literally freezing, that is 1 atmosphere of pressure. So as you are watching this, we are at a higher elevation than 0 at sea level. And depending on the temperature for the day, the pressure also changes. So we are not exactly at 1 atmosphere now, but we can convert it using the barometric pressure for the day. 1 atmosphere is equal to not only 760 millimeters of mercury, but also 760 torr, 101.325 kilopascals. You should be or become comfortable with converting between each of these units, which actually we're going to do on the next slide here. Before we do that, let's get into STP. So STP is an acronym in chemistry that's really, really important, especially with gas laws. And STP is at standard temperature and pressure. And these are used for purposes of comparison of gases between scientists. So if we were doing a lab in our chemistry lab in Hawley, Pennsylvania in the middle of winter where it's really, really cold, and if we were doing that lab and we were to collect a gas, we have to consider the temperature and pressure that that gas is at, because somebody who does the same exact experiment in Hawaii in the middle of the summer where it's blazing hot, they might get a different volume. So we need to compare those volumes to one another, considering we're at 2 different temperatures and pressures. So scientists came up with this, this standard temperature and pressure. And the standard temperature is 0 degrees Celsius. And 0 degrees Celsius, the same as 273 Kelvin. And the way to convert degrees Celsius to Kelvin is you literally add 273. It's a very simple conversion. It's not even a conversion. You just add 273. So 1 degree Celsius is 274 Kelvin. 10 degrees Celsius is 283 Kelvin, which is right there. So Kelvin temperature is equal to your temperature in degrees Celsius plus 273. And your standard pressure is at 1 atmosphere. So again, so that would be at sea level at 0 degrees Celsius. So chemists use this as a means of comparison in order to compare their data to one another to make it more reliable. Let's go ahead and do some sample calculations going from the different units of pressure, which we went through on this slide right here. So sample problem 1, let's go ahead and do that. So here is sample problem 1. So we're just going to do a very basic pressure conversion here using this little section right here. Like I said, this is the one that I like to kind of keep an eye on because this tells you all of the relationships between the different units of pressure. And unfortunately, with pressure, there are a lot of different ways that we can measure that. So you won't have to memorize these values, though I think just by using them so often, you'll probably end up memorizing them. Every now and then, you might have to use a PSI too. So PSI is down here towards the bottom. So just keep that in mind. Anyway, the average atmospheric pressure in Denver, Colorado is 0.830 atmospheres. We want to know this pressure in millimeters of mercury and kilopascals. So we're just going to do a very simple dimensional analysis problem like we would do in Chem 1. So 0.830, and we have units of atmospheres. So let's go ahead and convert this. Let's convert it to millimeters of mercury first, just because that's listed there. Atmospheres to millimeters of mercury, which means that units of atmospheres cancels. And if I look here, this tells me right in this first row that 1 atmosphere is equal to 760 millimeters of mercury. So 1 atmosphere is equal to 760 millimeters of mercury. So if we multiply these by one another, we get an answer of 631 millimeters of mercury. And that makes sense because Denver, Colorado is not at sea level. So if sea level is down here, let's say, so this is where you would be at in Hawaii, right? So here's a very poorly drawn palm tree. And if you're in Denver, Colorado, so you're all the way at the top of a mountain, let's say, if you're in Hawaii, there's a lot more pressure that's being exerted on a person that's surfing, let's say. There's a lot more pressure. There's a lot more stuff on top of their head, as opposed to somebody who's standing on the top of a mountain in Colorado. They're snowboarding down the mountain. There's not as much pressure that's being exerted on their head. So the pressure is much lower on top of the mountain, which is why you'll see that pressure is low. I visited Montana once, and I think with the pressure, because it was so much lower than what I'm used to, a lot of people tend to get like little sinus irritations. So you might experience that, and it all has to do with the pressure. Let's try this second one here. So we did millimeters of mercury. Let's go ahead and try kilopascals. So remember that all of this right here is equal to 1 atmosphere. So 1 atmosphere is also equal to 760 torr. 1 atmosphere is also equal to 101.325 kilopascals. But these are also equal to one another. So 760 millimeters of mercury is equal to 101.325 kilopascals. Ultimately, it doesn't matter which way you solve it. You could start off by converting millimeters of mercury to kilopascals, or you can convert it using the 0.830 atmospheres. I'm just going to go ahead and do this first one here. If you want, you can use that 631 because, like I said, we should get the same exact answer. So I'll put a 1 down there as a placeholder. So we'll convert atmospheres to kilopascals. And according to this right here, 1 atmosphere is equal to 101.325 kilopascals. 101.325, and they cancel. And when you solve for that, you should get an answer of 84.1 kilopascals. Remember to follow your significant figures. So in this case, we're going to assume that 760 is infinite. I'm actually not 100% sure if it is infinite or not. It might not be, but we're just going to assume that it is, because I always like to use the measurement more so as the means of determining significant figures. So 0.830 has 3 significant figures, and so should your answer for both of them, actually. And then we have the gas laws. So the gas laws, we are going to relate temperature, pressure, and volume to one another in these mathematical relationships. So simple mathematical relationships between the volume, the temperature, and the pressure of gases. So the first one that I want to talk about is Boyle's Law. And Boyle's Law relates your pressure and volume to one another. So it states that the volume of a sample of gas at a given temperature varies inversely with the applied pressure at constant temperature. So temperature stays the same when we're comparing Boyle's Law. The temperature is the same throughout. And here's your equation. So P1V1 equals P2V2. The pressure and volume of one sample of gas is equal to the pressure and volume of that same gas, but when one of them changes. And when pressure goes up, your volume is going to go down. So think about it. If I increase the pressure, if I take a sample of a gas and I make those particles come closer together to increase the pressure, the volume has to go down. So these are inversely related to one another. And I usually think of Boyle's Law, and I remember it. This is like kind of sick, but this is literally how I remember it. If you have a boil on your face or like a pimple, you usually do this, right? And you do that to get rid of the boil because you increase the pressure. You're trying to put a lot of pressure on that, right? You're increasing the force per unit area in order to decrease the volume. Makes perfect sense. You got a boil, increase the pressure to lower the volume. Temperature is constant. You're not changing the temperature of the boil, but you're changing the pressure conditions, which in turn affects the volume. So here's a nice little image that shows that as well. So if I have this container at some pressure, if I decrease the volume, the particles have to become closer to one another. And notice how the pressure is increasing because these particles are colliding with the container walls more often. So here, this really isn't showing that they're colliding with the container walls. But notice with the one on the right, this one is colliding with the wall. This one is colliding with the wall. And that's what pressure is. It's the pressure per unit area, or in chemistry, it's the pressure at which these particles kind of exert on the walls of the container. Let's do sample problem 2, which is 2 equations that deal with Boyle's Law. So sample problem 2, dealing with Boyle's Law. So there's your equation that's given to you. And here's a nice little image as well that's represented here for you. So notice how in both of these two systems, so this would be system 1. We'll just call this one right here system 1. And this one right here is system 2. Notice how temperature is the same for both of these. And when temperature is the same, we say that temperature is constant. So temperature is constant throughout this whole thing. And if I notice, the volume is decreasing. So the volume is going down by about half. So if it's going from a volume of 4, whatever units this is, it's not telling me. It's going from 4 to 2, so it's going down by half, which means that the pressure is actually doubling. So it's going from a pressure of 1, whatever the unit is, to a pressure of 2, which shows that when volume decreases, the pressure is increasing. And remember that the temperature is not changing. but pressure is a measure of how much those particles are bouncing off the container walls. So in this one right here, you have more particles that are hitting the walls of the container, which is why the pressure is going up. In fact, they're hitting the walls twice as much because the pressure is doubling. Let's go ahead and try sample problem 2A together, and then you'll do 2B on its own, because the math with each of these is actually pretty simple. A sample of oxygen gas has a volume of 150 milliliters when its pressure is 0.947 atmospheres. So we're going to say that that's V1 and P1. What will the volume be of the gas, or what will the volume of the gas be at a pressure, so we're changing the pressure here, of 0.987 atmospheres, assuming that the temperature remains constant? Sometimes when I start doing new equations, I like to take that word equation and I just write down all the variables that I have. So that's what I was doing as I was reading that problem. I have this gas that has a volume of 150 milliliters at a pressure of 0.947 atmospheres. I want to know what's the new volume when I increase that pressure just a little bit. And we should see that the volume goes down. Let's go ahead and plug these into Boyles Law. So Boyles Law says P1 V1 equals P2 V2. So 0.947 atmospheres at a volume of 150 milliliters. We want to know at 0.987 atmospheres, what's the volume? So we're solving for V2. Once we get to this, we're doing just some basic algebra here. And actually with Boyle's Law, we don't have to change any units. Whatever unit your volume is in, it's what it's going to be on the other side. Same thing goes for pressure. So volume and pressure units don't matter. They just have to be in the same units. So because my volume, my V1 is in units of milliliters, that means that my V2 must also be in milliliters. I'm not going to go through the work with you, but if you need help with solving these questions, just let me know. I'll be more than happy to show you how to do it on a calculator. But your answer for V2 should be 144 milliliters. And that makes sense because since the pressure went up, that must mean the volume must go down. So it is going down by about 6 milliliters, which is not very much. And that's because the pressure is not increasing very much. And that's it, using Boyles' Law. So how about you use that same exact equation and try sample problem 2B. So pause this video, try sample problem 2B. I'll have the answer up here when you come back. And there is your answer for B, 3.18 atmospheres. Again, if you are getting a different answer, but you have the work set up correctly, just let me know when you come to class, because it's probably just how you're typing it in the calculator, and that's an easy fix. If you have the work set up correctly, but the answer is wrong, no problem. I'll show you how to type that in the calculator correctly. Next is Charles's Law. So very similar, but it does have something slightly different about it, which you're going to see with a lot of these. They're all very similar, but slightly different. That's because they're all derivations of the same thing, essentially. Charles's Law states that the volume that's occupied by any sample of gas at constant pressure, so pressure is the same here, is directly proportional to the absolute temperature. Absolute temperature is the temperature in Kelvin. So that's what absolute means. It's always in units of Kelvin. And here is your equation. So V1 over T1 equals V2 over T2. So the volume of some gas at some temperature is equal to the volume of that same gas at another volume at some temperature. And these are directly proportional to one another. So here's a nice little image down below. These are some balloons that this chemist is putting into a vessel of liquid nitrogen. And liquid nitrogen is very, very, very cold. I don't know exactly what temperature, but it's very cold, trust me. So you take these balloons and you stick them in a vial of liquid nitrogen. You'll see that all of these balloons can fit in this sample right here. That's because when the temperature decreased, the volume of that gas also decreased. So when temperature is going down, since temperature is a measure of kinetic energy, those particles are not moving as fast, and therefore they don't need to occupy as large of a volume. So here, when temperature goes down, the volume goes down. And once you take these balloons out and that temperature increases again, the volume is also going to go back up. It's really cool, actually, to think about. You could fit all of these balloons in this tiny little sample of liquid nitrogen. And pressure is constant. And that's because the pressure that this is happening at is constant. This is at atmospheric pressure, or the pressure of the room. So the pressure of the room is not changing, which is why that is held constant in this case. So Boyles' law, pressure and temperature are inversely proportional. One goes up, the other goes down. In Charles's law, they are directly proportional. When one goes up, the other also goes up. Let's do sample problem 3, all dealing with Charles's law. So here is Charles's law. Again, I just have that equation up on the screen. Unlike Boyles' law, where the units for pressure and volume don't matter, they don't matter for volume here, but temperature must be in units of Kelvin. So just write that down here. Temperature must be in Kelvin. Because if you think back to that definition, the definition is that it's an absolute temperature. So just be careful. Temperature must be in Kelvin for any and all gas law problems. So knowing that, let's go ahead and try sample problem 3A together. So a sample of neon gas occupies a volume of 752 milliliters at 25 degrees. What volume will the gas occupy at 50 degrees if the pressure remains constant? So notice here that you actually have the temperature that's in units of degrees Celsius. And this second question is important. I put that in there because I wanted you to see this. But it says, why does the volume not double? Even though the temperature is doubling in degrees Celsius, it's actually not doubling in Kelvin. That's why this is so important to put this in Kelvin, units of Kelvin for temperature. Let's get all of our units down here. So V1 is equal to 752 milliliters, and my temperature is at 25 degrees Celsius. But remember, we do have to convert it to Kelvin. So 25 plus 273 gives us 298 Kelvin. What volume will the gas occupy at 50 degrees if the pressure remains constant? So we do have to convert 50 to Kelvin. So 50 plus 273 gives you 323 Kelvin. And remember, with this, we said pressure is constant. This means pressure isn't changing. So in this case, the atmospheric pressure is constant throughout this whole entire thing. Let's go ahead and plug everything into Charles's law. So 752 milliliters over 298 Kelvin is equal to, we want to know the volume, at 323 Kelvin. So notice how the Kelvin temperature, it's not doubling. So that's important. When you solve for this, you'll find that the new volume is 815 milliliters. So that is the volume of the gas when it increases by 25 degrees Celsius. But the volume is not doubling because we have to consider this as an absolute temperature. So we have to use the absolute temp, which is in units of Kelvin. if you were to have units of Kelvin temperature, let's say 200 Kelvin to 400 Kelvin, because your Kelvin temperature is doubling, then the volume would double. If you do decide to take AP, that's an important question. There are so many times that I see students get tripped up on questions like that because they don't recognize the fact that it has to be in Kelvin temperature. So put a star next to this one because this is important. This last section right here, why does the volume not double? Kelvin temperature. You go ahead and try 3B. So pause the video, come back, and let's see if you get the right answer. And there is your answer for B. So remember, you did have to convert to Kelvin temperature, and you have to convert it into Kelvin temperature to get an answer in Kelvin, but remember to read the whole question. So it is asking, what is the outside temperature in degrees Celsius? So once you get that Kelvin temperature, you could subtract 273 and get an answer of -11. Another reason why you can't use the degrees Celsius in any of the gas laws is because in order for the math to work out, you would get a negative volume. So you can't have a negative volume. If this was -11 degrees Celsius, you would have to have a negative volume, and that's literally a vacuum. So it doesn't exist, which is why you always have to take these calculations out of degrees Celsius. And the last law we're going to talk about in this video is Gay-Lussac's law, which kind of takes Boyles' law and Charles's law and puts them together to make something new. So Gay-Lussac's law gets rid of that volume relationship here. So this is a pressure-temperature relationship. The pressure of any sample of gas at a constant volume is directly proportional to the absolute temperature. Looks very similar to Charles's law, but it does not have that volume in there. So here's the best example that I can think of. It's actually, in my experience, it's difficult to think of a Gay-Lussac's law application, but this one works. So if you have a can of soda in a car in the summer, that can of soda has carbon dioxide bubbles in it, right? So it's got those gas particles that are in there. And that can is at a constant volume, right? So those gas particles that are in that sealed container have a constant volume, which is why the volume is not changing. But as the temperature of that can increases, the pressure inside of that can will also increase. And it will increase until the can no longer withstand that pressure, and then the can will explode. This is Gay-Lussac's law. You might also see this with a bag of chips, maybe outside on a barbecue on a day you're having a cookout. The air inside of that bag of chips gets so warm, the pressure will increase until the bag pops. So directly proportional to one another. When temperature increases, because it's a measure of kinetic energy, the gas particles are moving much more frequently. The pressure is increasing. They're colliding with the container walls more frequently. Let's go ahead and do sample problem 4, dealing all with Gay-Lussac's law. So I did change some of the pictures after I kind of went through the PowerPoint, and I found these pictures I like a little bit better, but here's a nice representation of Gay-Lussac's law. So notice here that when I raise the temperature, so here we're applying heat to this, these particles are moving faster, which means they're colliding with the container walls more often. And you'll notice that both of these systems are at the same volume, and that means that volume is constant. So volume is constant for Gay-Lussac's law. Every one of these laws has something that's constant. And we just have to remember that if you are analyzing questions that have to deal with each of these problems. We still have to convert temperature to Kelvin. So let's go ahead and dive into sample problem 4A. The gas in an aerosol can is at a pressure of 3 atmospheres. So we'll say P1 is equal to 3.00 atmospheres at 25 degrees Celsius. 25 degrees, which again, we'll just convert that straight to Kelvin. So 25 plus 273 is 298. Directions on the can warn the user not to keep the can in a place where the temperature exceeds 52 degrees Celsius. What would the pressure be in the can at 52 degrees Celsius? So at what pressure will this can explode is what it's saying. Let's convert 52 to units of Kelvin, and the answer there would be 325 Kelvin. Units of pressure doesn't matter. So because I'm plugging in atmospheres, that means my pressure units will also be in atmospheres. So let's go ahead and just start solving there. 298 Kelvin equals P2 over 325 Kelvin. And if you solve for this correctly, you should get a pressure that's equal to 3.27. So again, this is another question that you might be able to get tripped up on. So notice here how the volume is a little bit more than doubling. A question you might see is what happens to the pressure? Does it double? Does it do this? Does it do that? The pressure does not more than double, and that's because we have to consider the Kelvin temperature. So it's actually only going up by a fraction of that. And when the temperature increases, so does the pressure, and you'll see that it does. Last problem, go ahead and try 4B, pause the video, come back and see what you get. And there's your answer for 4B, so 36 degrees Celsius. Something to keep in mind here is that notice the original pressure is in atmospheres and the final pressure is in units of PSI, pounds per square inch. So you do have to get both of those pressures in the same unit. It doesn't matter what unit, I just happen to convert the PSI unit to atmospheres, which you'll see my work down here for that. If you converted both of these to units of PSI, you should get the same exact answer. So it doesn't matter what units they're in, as long as your pressure units are the same, ultimately you'll get the same exact temperature. Just be careful though, the question is asking what's the temperature in degrees Celsius. So once you get that Kelvin temperature, make sure you subtract your 273 to get your 36 degrees. Like I said, I think the biggest issue I see with these gas laws is students just not plugging them in the calculator correctly, and that's an easy fix. So if that happened to you, there's no need to stress, no need to panic. Just stop by and see me, come ask me a question. I'll be more than happy to help you. And if you have any questions on anything, make a note somewhere in your note packet, put a star next to there or highlight it, and make sure you ask me during the next class. Anyway, that's it for this video, and I will see you in the next video, which we continue with the gas laws, combined gas law and Dalton's law of partial pressures. See you then. Bye.